All right, in the last video, we talked about how the central limit theorem and the law of large numbers help us understand what is probably going to happen, what's going to be likely to happen, what's the mean, what's the standard deviation, and the central limit theorem tells us the shape of the distribution. When can we use a normal distribution? Answer, when the sample size is big enough, okay? The law of large numbers says bigger sample sizes will be more likely to be closer to the truth, to the population mean or the population proportion. Now in this video, we're going to focus on sample means. So when I do calculations with sampling distributions, I start with two rules, Rule 1 and Rule 2. Rule 1 is for sample means. Rule 2 down here is for sample proportions. A sample mean is when you are asking a question and the result is going to be a number. Like, what's your income? What's your height? What's your weight? What's your IQ? And your goal of the study is to calculate an average height, an average income, or an average weight, for example. Sample proportions are when you're asking a yes or no question. Will you vote for this certain candidate? Or do you support this proposition or this new law? Do you think we should help the poor more? Yes or no questions. We're going to summarize that with a proportion that say yes or no to the question, okay? Let's start off with looking at sample means, though. We know sample means will have a normal distribution. This is from the central limit theorem, with a mean equal to the population mean of the thing we're studying on average, right? Sometimes higher, sometimes lower, but on average you're going to be right. And the standard deviation of the sample averages will be equal to the standard deviation of the data you're studying divided by the square root of n. That comes from the law of large numbers. When either of these two things are true. So the point is, don't use the normal distribution unless you can either say that A is true or B is true. A says the individual data we're studying has a normal distribution itself, and we know the population standard deviation of that distribution. And we'll go through a couple of cases to look at what this means. Or B, suppose you're studying something where the data you're studying are not normally distributed. Then, if you know the population standard deviation, you have to, you can make up for the fact that the data you're studying is not normally distributed if your sample size is big enough. 30 is usually big enough. So what we're doing in Rule B is we're using the central limit theorem, CLT, central limit theorem, that says if you add up or average a large number of things, those totals or averages will have a normal distribution. So that's what B is taking advantage of. A says, well, you know, if you're already studying a subject like IQ or height or weight or the length of pregnancies, if you're already studying something that's normally distributed, it doesn't matter what the sample size is. The sample size could be 1, and it's already normally distributed. A sample size of 2, still normally distributed. 100, still normally distributed. As long as you know the population standard deviation. Now, if you don't know the population standard deviation, then what do? Well, that's a subject for another video. But the short answer is use the t-distribution. But we're going to assume for now we know the population standard deviation. Now here's another question. What if the data are not normally distributed and the sample size is smaller than 30? What should you do? You basically have two choices here. Choice 1, get a bigger sample size. So get more data. What if you can't get more data? Then your second option is get a PhD in statistics or hire someone with a PhD in statistics. That's a difficult problem. So, and this is something that I would not want to deal with. A very small sample size of a very skewed distribution, say that's not normally distributed. I would consult someone who knows more about statistics than I do in that case. or I would just get more data. Normally that's easier. Okay, let's assume we're not dealing with any of these problems down here. Let's assume just we can either use rule A or B. Let's look at two different cases where we can do that with sample means. First, let's look at a case where A will come into play. What if we're studying something where what we're studying already has a normal distribution, like IQ? Let's take that for example. And we know the population standard deviation of IQ. It's 15. So let's look at that problem. So here's a typical kind of problem you might want to study. You know that IQ is normally distributed. Here's a little shorthand for distributed, a little tilde or squiggle, is distributed with a normal distribution. The average IQ is 100 and the standard deviation is 15. Okay? Sometimes when people write a distribution like this, they'll put the mean and the standard deviation, but be careful, sometimes people will square that and put the variance there. So we know that, and we want to know if we take a sample, if we sample 100 people from this population, say n equals 100, and we're going to calculate a sample mean, we average those 100 people, what is the probability? What is the probability that our sample mean, x bar, is going to be somewhere between, and let's just make up a range here. Let's say between 98 and 102. Okay? Another way of asking this question would be to ask, what is the probability that our sample mean is within 2 of the truth? What is the probability our sample mean is within 2 of the truth, the population mean, right? So this is another way of phrasing that question. So how are we going to attack this problem? Well, the first thing you want to do is check to see that rule A or rule B applies. And rule A is going to apply here because IQ is normally distributed to begin with, and we know the population standard deviation is 15. So we're good to go. What we know then from rule A is that these sample means are going to have a normal distribution, no matter what the sample size is, because IQ is already normally distributed, and the mean of the sample means. So let's be clear on what we're drawing here. The mean of all possible sample averages of 100 is going to be 100, the average IQ. All right? So this is not the sample size of 100. This is this 100, the average IQ. There's no reason to think that the average of 100 people's IQs should usually be more than 100 or usually be less than 100. You know, sometimes more, sometimes less, but on average we'll get it right, okay? So that true population mean goes there. What's the standard deviation of this normal distribution going to be? What we call the standard error, or the standard deviation of sample means. Well, all we do is we take this standard deviation of IQ, 15, we have to adjust it for the fact that we are averaging 100 people together. So we divide it by the square root of n. So the standard error for a mean is the standard deviation over the square root of n. So let me just fill in 100 there. And that's going to be 15 over 10 is 1.5. So that means that when we look at this normal distribution for where do I think my sample averages will be, one standard deviation below is 98.5, 1.5 below, and one standard deviation above is going to be 101.5, and 68% of the time our sample means should be in this range, all right? But that's not what the question is asking. The question asks what percentage of the time will we be within plus or minus 2, within 2 of the truth. And so what we want to do is say, well, my boss wants to know what's the probability will be, our sample mean will be somewhere between 98 and 102. I should have drawn that line about the same distance as the 102 one. But so let me try to do that here. All right. So we want to know what's that probability. At this moment, we're back in a regular old normal distribution kind of problem. We draw our picture. We calculate z-scores. What's the z-score for 98? Well, it's going to be 98 minus 100 divided by the standard deviation of 1.5. And that's 2 over 1.5. That's going to be minus 1.33. This z-score is going to be 102 minus 100 divided by 1.5. Let me just make sure I'm doing that in my head here. Yeah, 1.33. That's going to be a z of positive 1.33. And so what we need to do is we need to take those to our z table and look them up. So let's do that. So here's our normal distribution table. Let's look up a z-score of minus 1.33. 0, 1, 2, 3. We get 0.0918. Go back to our picture, and that tells us that this probability is 0.0918. Now, normally, what we would do in this kind of situation, and we can do it this way, is we would look up the positive 1.33 in the z-table. And we would get this area of being less than 102, subtract off this area, 0.0918, and we'd get the area in the middle. You can do it that way, and that works perfectly well, but let me show you a little shortcut. Because in this problem, 98 is the same distance away from 102, and this z-score is just negative, and that's positive, the same number, we can use the symmetry of the normal distribution to say, well, if this area is 0.0918, then this is 0.0918. So how much is going to be in the middle? Well, remember that idea of alpha, if you watched my normal distribution videos. Alpha is the total amount that's not in the middle, and that's 2 times 0.0918. So that's 0.1836. That's the total amount that's not in the middle. How much is in the middle? Well, 1 minus that. 0.8164. And so that's a little bit quicker way to do this problem, where you only have to look up one of the two z-scores, and then you use the idea of the symmetry and alpha. Okay? Now, that's what we do if we're studying something in case A. The individual data we're studying is already normally distributed. Well, what if it's not normally distributed? Like income, for example. So let's go and look at another problem. Suppose our job is to take a sample of some data from people's incomes. Now, incomes are not normally distributed. They are very skewed right in every data set I've ever seen. Why? Well, most people earn kind of a small to moderate amount. There's this big hump here in the middle, but then there are a few people that make an awful lot of money. Okay? So let's suppose here's what incomes look like. The mean is 100,000, just to keep the numbers simple here. And the standard deviation is 20,000. But it's very skewed. We're not studying something that's normally distributed. And here's 0, and a few people will make less than 0, but not very many. And that's one reason why this distribution is pretty skewed. To make less than 0, you have to, say, own a business and lose a lot of money, for example. Suppose what we're going to do is we're going to take a sample of 100 people's incomes, and we're going to calculate the average income of the sample. Question is, what's the shape of this distribution of averages going to be, and how close do we think the average is going to be to the truth? And our boss asks us a question. He says, hey, guy, I want you to calculate what is the probability that the sample mean of incomes, and let me just write this the short way. What's the probability the sample mean of incomes, x bar, is within say, I don't know, $1,000 of the truth, the population mean. How do we calculate that probability? Well, let's go check our rules up here. So as we mentioned, Rule A is not going to work because the individual data we're studying is not normally distributed, so that throws that out. Rule B says if the data you're studying is not normally distributed, as long as you know the population standard deviation and your sample size is at least 30, you're good to go. That your sample averages will still have a normal distribution with a mean equal to the average of the original data, and the standard deviation of your sample means, or your standard error, is equal to your standard deviation of your original data divided by the square root of n. All right, what does all that mean? Well, let's just do this problem here. What that means is that when we calculate sample means, the sample means won't be skewed because we have such a big sample size. The central limit theorem takes care of that. But the mean is still going to be 100,000. But now the standard deviation of our sample means is going to be equal to the original standard deviation, 20,000, divided by the square root of n. 100 in this case. It could be 30, it could be 1,000. As long as it's anything over 30, we can legitimately do what we're doing here. So 100 is a nice easy number to take the square root of, so we'll use that. So that standard deviation is going to be 20,000 over 10, which is 2,000 now. Okay? So this question wants to know what's the probability a sample mean will be within 1,000. Okay, well let's draw our picture, calculate our z-scores, go to the table, etc. So 1,000 is going to be fairly close in here to 100,000. So we're asking what is the probability we're between 99,000 and 101,000, okay? So what do? Well, z-scores. So what's the z-score for 99,000? Z equals 99,000 minus 100,000 divided by 2,000. That standard deviation of the sample means. So what we're going to end up with is minus 1,000 over 2,000, which is going to be minus 1/2. So z equals minus 0.5. What's the z-score for this one going to be? Positive 0.5, because it's the same distance away from the mean. So z equals positive 0.5. Now we could just as easily do problems that we're not looking at the same distance around the middle. All I'm saying is it's the most common kind of question you'll want to answer is some symmetric region around the middle. But you could use the same technique to do any area. We could answer what's the probability our sample means above 101,000, for example. But what do? Well, we need to round this z-scores to 2 decimal places, and now we'll go to our table. So let's look up that z-score of minus 0.5 here. So negative 0.50. Whoops, sorry, I'm dragging this around and it's not cooperating. Here we go. Minus 0.50, 0.3085. And again, probabilities you get from the table are always less than probabilities. So let's take that 0.3085 back to our picture, and that's the probability of being down here. Now, as I mentioned last time, we could now look up the positive z-score and get this larger probability of being below 101,000 and subtract the two, but a little bit quicker method for this kind of problem is if there's 0.3085 there and we're looking at the same distance and the same z-score on both sides, just one's positive, one's negative, then there's going to be a 0.3085 here, making the total amount that is not in the middle, what we call alpha, let's see, 0.617. And so if the total amount not in the middle is 0.617, 1 minus that gives us that 0.383 is in the middle. So if your boss asks you, what is the probability that our sample mean is going to be within 1,000 of the right answer, the truth, you have to give them the bad news. With a sample size of 100, only about a 38.3% chance of that happening, boss. So here comes the point of looking at this kind of problem. Suppose your boss is upset that there's only a 38.3% chance of that happening. What's your advice? Well, boss, all you got to do is get a bigger sample size, and then when we calculate this standard error, it's going to be something smaller than 2,000, and that's going to make these z-scores bigger, and that's going to bring these, this range out wider here to where there's a higher probability of being in the middle when we draw our picture and we do that calculation. So if instead we had a sample size of 1,000, you're going to be more accurate. And again, that's the idea of the law of large numbers. Bigger samples are more likely to be more accurate. So that's how you do these problems with sample means. In the next video, we'll look at how to do a problem involving proportions and how accurately your sample will estimate a proportion.